All right, so let's finish this last question here, letter F. I know that I didn't get to go over this in all classes. So we have here 2/3 x plus 4 equals 1/3 x plus 12. So if you want to get rid of all of the fractions, you totally could. Since the denominators are both 3, you can multiply literally every single term by 3, and then the fractions will disappear. But I actually don't think it's that bad to deal with them since they have the same denominator. So what I'm going to do is move this one to the other side, cancel it out by subtracting both sides by 1/3 x. When I do that, this goes away. 2/3 minus 1/3 is 1/3, so I have 1/3 x plus 4 equals 12. Next thing I'm going to do is subtract 4 from both sides. I get 1/3 x is equal to 8. And then the last thing I can do is either divide both sides by 1/3, since that's multiplication, or I can multiply by the reciprocal, which will cancel out 1/3 to make it the coefficient 1. So you can also just multiply by 3. And that cancels these out, and I'm left with x equals 24 for this last example. All right, if we turn this over to the next page, we will see the last section in this little section of 2.1, and we have some special cases we're going to review. So there's two types of situations that can happen that make equations kind of weird and different. So something that can happen is when you have the variables are equal on both sides, like you have a 2x on the left and a 2x on the right. And if you have the same variables, when you go to solve it, they'll cancel out, and you're either going to be left with a true statement or a false statement. The identity is an equation whose solution set is true. That means you have a true statement. No solution means that the equation has no solution for that particular variable. So let me show you examples of both. 6 parentheses x plus 3 equals 6x plus 3. If I go to solve this, the first thing I would do is distribute. 6 times x is 6x. 6 times 3 is 18. So I have 6x plus 18 equals 6x plus 3. Now, I already know that this is false. This can't happen. 6x plus 18 does not equal 6x plus 3. There's no number that will be able to do this. But if we were to solve this, I would subtract 6x from both sides. The variables cancel out. I'm left with 18 equals 3, which is not true. 18 does not equal 3. So the answer to this problem is no solution. Right? For the next one, 3x plus 11 minus 6x equals 11 minus 3x. The first thing I'm going to do is try and solve this. On the left-hand side, I can combine 3x with negative 6x. And when I combine these together, this turns into a negative 3x plus 11 equals 11 minus 3x. Now I can tell just from looking at this that these two things are equal because I have a negative 3x on both sides and a positive 11 on both sides of the equal sign. But if I was to solve this, I would add 3x to both sides. When I do that, I'm left with a true statement. 11 does equal 11, so that this answer is considered the identity. Or you can call it infinite solutions. Depending on the textbook, some textbooks call it the identity, some problems will say infinite solutions. So they mean the same exact thing. All right, the next two problems look like they're going to be kind of crazy because they have graphs, but they're really not that crazy. So let's look at the next ones together. I'll read it. I'll show you how we can solve it from algebra and how we can solve it with the graph as well. So let me just erase this. All right. So the problem says, the average annual expenditures per student Y in dollars for primary and secondary public schools in the United States from 1998 to 2005 can be approximated by the model Y equals 355.3 T plus 3,725, where T is between 8 and 15, and T represents the year, so like T equals 8 really means 1998. According to this model, which During which year did the expenditures reach $7,633.30? Well, that's a lot. So basically we have this crazy equation, right? And it's y equals 355.3t plus 3,725. All right, and it's asking us the question, which year did the money reach that amount of money? Okay, so we know here from the problem that t is representing time, which is years. So we are trying to solve for that variable, for t. We know here that what this equation is equaling to is the amount of money. So it says the annual expenditures per student in dollars. That's what the y variable stands for. So when we go to solve this, we are going to substitute this number here in for y because the y is representing the amount of money the equation is equal to. So I'm going to replace in 7,633.30 into this equation, and then I'm going to solve for t. So this looks crazy because we have decimals and stuff, but it shouldn't really be that bad. The first thing I'm going to do is subtract 3,725. Right? When I subtract this, and you're definitely going to want to use your calculator, I'm plugging it into mine right now, 7,633.3 minus 3,725. We get here 3,908.3 is equal to 355.3t. All right, and then the last thing we're going to do to solve for time, for t, is divide by 355.3. And we're going to get t is equal to 11. So this means that it's 11 years after the starting point. So we know that year 8 means 1998, which means that's our starting point. 1998 is the starting point. So if we're looking at 11, this would be 3 more than that. So 1998 plus 3 is going to end up being 2001. So 2001 would be the final answer then for this one, since we are looking for year 8 is 1998. This is 1999, 2000, 2001. So here is where we would be, 2001. We can also tell from the graph that the answer would most likely be 11 or 2001, because looking at the bar graph here, we can look for the bar that's in between 7,000 and 8,000, and it's this one right here. So we can kind of see from the graph as well that it would be that problem. Okay, similar to this one, we have a second word problem, and I know when you see word problems, you probably feel a little nervous about it, like it's going to be super difficult, but it looks like it's crazy. It's really not, though. I don't know why this is not erasing. Okay. All right, so let me just read the second one. The annual sales Y in billions of dollars of food and beverages at full-service restaurants in the United States from 1998 to 2005 can be approximated by the model y equals 6.37t plus 67.5. And again, they're giving us this inequality to show that it's between 8 and 15, where t represents the year and t equals 8 represents 1998 again. So we are trying to figure out when the annual sales will equal 125 billion, and we're going to explain how to find this answer graphically and algebraically. All right, so if we were looking for the algebraic answer, we would solve this equation. So the equation is representing sales in billions of dollars and years. And the equation is y equals 6.37t plus 67.5. We know that on a graph, the y-axis is here, so we know that the y is representing the sales in billions of dollars, and t is representing the years here. So when they're asking us to figure out the time for when the sales is equal to 125 billion, I know we'll have to replace 125 in for y. Now, because these numbers are in billions, you don't need to use all of the zeros. You just use 125. And rewriting the rest of the equation, we have 125 equals 6.37t plus 67.5. Then we would solve this. The first thing I'm going to do is subtract 67.5. All right, I get 57.5 equals 6.37t. And I'm going to divide by 6.37. And this one's not exact. This is why it says approximately. I'm going to get that the time is about 9. So looking at the graph, we're looking at here, this is the bar we would be looking at, which I can see is a little bit above 120, so it looks like it would be 125. So technically, it would be year 1999, since it's about 9. All right, if we flip this over to the next page, the last thing we're going to do is try some practice problems with the graphing calculator. Now, I know many of us might not have a graphing calculator right now. Hopefully, you will be able to purchase one because they really are helpful. I can tell you that I got my graphing calculator while I was in high school, and it lasted me all the way through college, and I eventually upgraded to the newer ones because I'm a math teacher, but it still does work. It's just an older version. But if you don't have a graphing calculator, you can actually get a graphing calculator free on, if you look up Google, if you Google Texas Instruments, you can get a free trial. I think it's 90 days. It's better than nothing, though, until we come back into school, and I can let you guys borrow one if they are going to let us do that this year. So I'm going to open up my calculator as well so I can use this because it's going to ask for, see, I'm using my free trial right now, too. It's going to ask for us to solve it with a graphing calculator, which will be interesting. So we are going to use the table feature of a graphing calculator to solve this equation. 7x minus 2 equals 4x plus 13. So here's how this is going to work. You're going to go into the y equals screen right here, and you're going to type in both of these little equations. We want to see when these equations are equal. When 7x minus 2 is equal to 4x plus 13. Now we can solve this algebraically by subtracting 4x from both sides, then adding 2, and then solving for x from there. Or we can put both of the little equations into two different y equals categories, and then you would hit second, graph, and it's going to open up to a table of values, and basically you're looking for when these values, in my case, in the blue and red, are equal. So these aren't equal, this is not equal. I'm looking down the line and I see right here they are equal. 33 and 33 are the same when x is equal to 5. So I can verify that for this equation, these two things are equal when x equals 5. And I can verify that with algebra if I replace in for the equation 7x minus 2 equals 4x plus 13. I can replace in a 5 for both of these, and I can verify that these are going to be equal since 7 times 5 is 35, and 35 minus 2 is 33. 4 times 5 is 20. 20 plus 13 is also 33, so I can verify that the answer is x is equal to 5. Now, if we didn't use the calculator to solve, we would just use the opposite of the order of operations, which is basically just the steps you would take to solve an equation, I would subtract both sides by 4x. I get 3x minus 2 equals 13. Add 2 to both sides. And divide by 3. I also get here x is equal to 5. All right, so for the last page, the last questions on the page, the you-try questions, there's 4 questions where I want you guys to solve to find the missing value of x. Now, not all of them will you be able to use the graphing calculator. You'll only be able to use it when it basically looks like that, where you have one equation equals another, like when you have variables on both sides. So that was just to show you how you would, but I want you guys to solve these algebraically. So try A, B, C, D on your own. And you can try the last one too. It explains how the graphing calculator wouldn't be that helpful. So you can try to do that one algebraically, and then we will go over these together. So complete the rest of the page basically, and then we'll go over these together soon.